True or false? The row space of a matrix A is equal to the column space of the matrix A transpose. True. Okay, the rank of A is equal to the dimension of what? The column space of A. Or what else could you have put? The definition is the dimension of the column space of A. Row A has the same, always has the same dimension. So you could have put row A here, and I'll accept it if you did. But the definition is col A. Okay, so the rank theorem says that the dimension of the column space of A always equals the dimension of the row space of A. And it says that the rank of A plus what always equals the number of columns in the matrix. The dimension of the null of A. That covers all the big stuff from this section. Okay, so today we're going to define the row space and the rank of a matrix and develop the rank theorem. So the row space of a matrix A, which we denote row A, is the set of all linear combinations of the rows of A. So you just treat the rows like vectors. It's natural to write them horizontally since they're already written that way, but you can flip them and make them vertical if that just makes more sense in your head, whichever you want. Each row has n entries as you go across because we're talking about an m by n matrix. So we have n columns, so there are n entries in each row. So row A is a subspace of Rn. So let's take a little look at this picture here. If this is a linear transformation T, this big cloud on the left represents the domain of T, which is Rn. And the cloud on the right represents the codomain of T, which is Rm. So the row of A is a subset of Rn. So it lives over here as a subset of the domain of T. And the row space of A is the same thing as the column space of A transpose. If you just take those rows and make them columns, now we're talking about a column space of the transpose matrix. So this picture has a bit more detail than your text gave, but I wanted it to be accurate. So the row space and the null space both live in the domain, right? They both live in Rn because linear combinations of the rows is going to live in Rn. We just talked about why. And the null space is the set of all things in Rn that get sent to the zero vector by the linear transformation. And then this is just a general x that lives anywhere in the domain, and it gets sent to A times x, which is in the range. So the range is not always the whole codomain. So I put it in this little subcloud. And the range of T is also known as the column space of A. The set of all linear combinations of the matrix's columns is what you get when you multiply A times some vector x, as you're taking a linear combination of the columns of A. And then the null of A transpose lives in Rm. And the column space of A and the null space of A transpose, the only vector they share is the zero vector. And over here, the null space of A and the row space of A, the only vector they share is the zero vector. Your book actually doesn't really go into that very much yet, but it'll be important in the future, so I wanted it to be in the picture. So this picture, I think, will help answer some of the questions that you have to do in your activities and in your homework. So you refer to this if you are confused about where different things live. Okay, so our first theorem said that if two matrices A and B are row equivalent, then their row spaces are the same. So if B is in echelon form, the non-zero rows of B form a basis for the row space of A and for B. So this is true because row operations are just taking, when you do a row operation, you're taking a linear combination of two rows, right? That's what a row operation is. You take multiply one of them by a scalar, add it to another one. That's a linear combination. So rows of B are linear combinations of rows of A, if B is the row reduced form. So thus, the row space of B is a subset of the row space of A. That's the definition of the row space. It's the set of all linear combinations. So B lives in A, but then row operations are reversible. So the row space of A is also a subspace of the row space subset of the row space of B. So it has to be that the two are equal. The row space of A equals the row space of B. Right? So if I say that B lives entirely inside A and A lives entirely inside B, they must be exactly the same size. That's the basis of the proof. So in practice, we use this theorem to find a basis for the row space of A, and we're also finding a basis for the row space of B at the same time. You row reduce A to a matrix B in echelon form, use the non-zero rows of B, not of A, to form a basis for the row space of A, and it also is a basis for the row space of B. Okay, so definition, the rank of a matrix A is just the dimension of the column space of A. And the rank theorem says that the dimension of the column space and the dimension of the row space are always the same, and that the rank of A plus the dimension of the null of A is always equal to n, the number of columns in the matrix. And this last part makes sense because the dimension of the column space of A is the number of pivot columns, and the dimension of the null space of A is the number of free variables, which only occur in non-pivot columns. So if you add up the pivot columns and the non-pivot columns, you should get the total number of columns. And we're adding some more statements to the invertible matrix theorem at the end of this section. If A is an n by n square matrix, then each of these statements are equivalent to the statement that A is an invertible matrix. The columns of A form a basis for Rn, because we already knew from the invertible matrix theorem that the columns of A span Rn and are linearly independent. So that means they're a basis, right? So that's just one logical step further. The column space of A is Rn. That's the same thing as saying the columns of A span Rn, which we already had as part of the invertible matrix theorem. The dimension of the column space of A is n. That's because all the columns of A span Rn and are linearly independent, so all of them form the basis. It takes all of them to form the basis. So if all of the columns are the basis and there are n of them, that's the dimension. The rank of A is n, because that's the definition is the dimension of the column space. The null of A has to be 0, right? Because if the dimension, if rank plus null, rank plus the dimension of the null has to equal the number of columns, then the dimension of the null has to be 0, right? If the rank is already n. So they're all provable using previous statements of the invertible matrix theorem plus the definition of rank or the rank theorem. And I just very briefly explained why they are. But you should spend some time thinking about why those things are true if it's not immediately clear. All right, so I have 3 matrices. I'm telling you from the start, they are all 3 are row equivalent. So give me an example of any vector in the column space of A. One, 0, 3, -3. Yeah. So the column space of A means linear combinations of the columns of A. So you can just throw weights on any of these vectors, any of these columns, and add them all up. So if I use 1, 0, 3, -3, that means I put a weight of 1 on here and a weight of 0 on every other column and added them all up. No. Nope. The column space of row equivalent matrices is not necessarily the same. That's why when we try to come up with a basis for the column space, we row reduce to figure out where the pivots are, but then you go back to the original matrix to take those columns, right? You can't take them from the row reduced matrix. Okay, give me an example of a vector in the row space of A. Sure, you just picked a random row from A. So it's like we're just putting a weight of 1 on this second row and a weight of 0 on the others. And it feels natural because it's already written horizontally to write this horizontally. Right? A vector where we just write out the entries going across. But if you're like, I can't deal with that, I've gotten too used to vertical vectors, you can go ahead and write this vertically. 0, 0, 1, 0, 0, 0, 1. Those two things mean the same thing. All right, how about a vector in the null space of A? Any vector that when you multiply A by it, you get the 0 vector. There's one vector that's always in the null space, all zeros. How big is it? What are its dimensions? 7. Yeah. This is a specific case, not n. So yeah. 7 zeros. Right? Because I can only multiply this 4 by 7 matrix by a 7 entry vector. Because you would take the column to multiply by the vector. Sorry, each row times the vector. And so 0 is always in the null space. The 0 vector is always in the null space of a matrix. Finding another vector in the null space of the matrix is going to take a little bit of work. Right? But you can always give the 0 vector. All right, what is the rank of A? The dimension of the column space of A, which is what? How'd you get 4? Okay, so that means that the column space is a subspace of R4, but it doesn't tell you the rank. The rank is the dimension of the column space, and we learned last class a shortcut for how to find the dimension of the column space was to look at the number of pivots. How many pivots are in the matrix A? 3. Yes, the number of pivot columns is the same thing as the dimension of the column space, which is the same thing as the rank. Okay, so the rank of A here is 3 because there are 3 pivot columns. 1, 2, 3 pivot columns. So the dimension of the column space is 3, which means the rank of the matrix is 3. What is the dimension of the null space? Well, what do the rank of a matrix and the dimension of the null space of a matrix always have to add up to? N. What is n in this case? 7. So it has to be 4. Yeah. There are 7 total columns here. The rank plus the dimension of the null has to add up to 7. So the dimension of the null must be 4. What's the dimension of the column space of A? 3. Tricking you, asking you the same question 2 different ways. And what's the dimension of the row space of A? 3, because they're always the same. The dimension of the row A and dimension of col A are always the same. And that number, the dimension of col A, also the dimension of row A, we call that number the rank. Okay, so col A is a subspace of, where do the vectors in the column space of A live? You told me a couple minutes ago. Nope. R what? R4 in this case. Yeah. So because the column space is just linear combinations of the columns of A, these are all 4 entry vectors, each of those columns. So when I take linear combinations of 4 entry vectors, I get a 4 entry vector. So the col of A is a subspace of R4, right? All the vectors in col A live in R4. Null of A is a subspace of what? R7. All, like, here's one entry from the null space. It was 0, 0, 0, 0, 0, 0, 0. 7 entries. Any vector in the null space, that's a vector that gets sent to 0, right? So it has to be in R7. This guy was in row A, and this guy was in col A. All right, row A is a subspace of R7. Yeah, we have this guy in row A, it's got 7 entries, so it's a subspace of R7. Okay, the column space of A transpose R7. It's the same question as row A, yeah. Because the column space of A transpose, you could always just replace that with row A. And we already answered that question, R7. The null space of A transpose, R4. How do you know that? Because columns becomes rows and rows become columns. So A transpose would be a 7 by 4 matrix. And you can only multiply a 7 by 4 matrix by a 4 by 1 vector. So elements of the null A are in the domain of the transformation, which is R4, once you take the transpose. And the row space of A transpose, where does that live? R4. How do you know that? What could I replace the row space of A transpose with? Column space of A. And we already answered that, R4. Okay, if I want to find a basis for the column space, the row space, and the null space, usually we do this first because the definition of the rank of the dimension is the number of vectors in the basis. But I'm doing it last because we were able to figure this all out, figure out all these dimensions using the rank theorem. So now my basis should have the correct number of vectors. Okay, who remembers how to find a basis for the column space of A? It's the pivot columns of A, right? You have to row reduce to figure out where the pivot columns are, and you take those columns from the matrix A. So my pivot columns are 1, 3, and 4. So 1, 3, and 4 of the matrix A form my basis for the column space of A. A basis is just the columns. The column space of A equals the span of all the vectors in the basis. So I'll write it like that. So col A is the span of the basis, right? And the basis vectors are 1, 0, 3, negative 3. 0, 1, 0, 3. And negative 1, 0, negative 2, 2. So the column space of A is the span of the basis, just these three vectors are called the basis, right? And the span of them equals the entire vector space. How do you find the a basis for the row space? Using B. Well, how do I use B? The non-zero rows of the echelon form. Yeah. And in this case, you don't go back to the matrix A. You just take the non-zero rows of the row-reduced matrix. That's going to be the row space, a basis for the row space of A and of B. 1, 2, 0. Those are too long to remember. 1, 2, 0, -1. -4, -2, 0. Oh, that one's not bad. 0, 0, 1, 3 zeros, 1. This is a basis for row A. Yep. And the span of the basis gives you the entire row space. All right, and then that last non-zero row is 3 zeros, 1, 4, 2, 0. So the three vectors themselves are the basis, and the span of a basis gives you the entire vector space. So these three vectors are the basis. You could pick C also. The non-zero rows of C also form a basis for B and for A and for C, row space. Yeah, it just has to be an echelon form. You take the non-zero rows of an echelon form. And the whole idea is that when you do row operations on a matrix, you're inherently changing the columns. So that's why when I'm doing the column space, I have to go back to the matrix A and take the pivot columns. But when you do row operations on a matrix, you're just taking linear combinations of the rows, and the row space is the set of all linear combinations of the rows. So it turns out that the row space of any two equivalent matrices is the same. Not the same for the column space. All right, so if I want to find a basis for the null of A, how do I do that? So the null of A is a set of all vectors that get sent to the zero vector. So the set of all vectors that give you an output of the zero vector, right? So I would augment with zeros. I would augment A with zeros, row reduce to reduced echelon form, right? And then I'd get the solutions, right? I'm trying to find all the vectors that get sent to 0. So I'm trying to find the solutions to AX equals 0. So I would have another set of zeros here when I row reduce. And then I have to put those solutions in parametric vector form. Okay, so this says x1 plus 2x2 equals 0. x3 plus x7 equals 0. And x4 plus 4x5 plus 2x6 equals 0. And which are my free variables? Yeah. x2, x5, and x6 and x7. I only had 3 pivot columns. All the rest of them have to be free. So I solved for my basic variables in terms of my free variables. And this says that x1 is negative 2x2. x3 is pivot, so I say x3 equals negative x7. And x4 is a pivot. No, it's not. This can't be all free variables. No, x4 is a pivot. Yeah, x4 is a pivot. So I solved for x4, negative 4x5 minus 2x6. And then I put this solution in parametric vector form. Okay, so x1 is negative 2x2. x2 is free, so I just put an x2 there. x3 is negative x7. x4 is negative 4x5 minus 2x6. That's x1, x2, x3, x4. x5, x6, and x7 are all free. So that's what a typical solution looks like. And then I break it out into parametric vector form. So x2 will be my first. The null space is the span of these 3 vectors I'm going to come up with. 4 vectors I'm going to come up with. x2 is free, and my next one I've got x5, x6, and x7. So my vector that goes on x2, I've got a negative 2 and a 1, then a 0, 0, 0, 6, 7. And then on x5, I've got 0, 0, 0, negative 4, 1, 0, 0. x6, 0, 0, 0, negative 2, 0, 1, 0. And x7, I have 0, 0, negative 1, 0, 0, 0, 1. Ooh, it's a lot of work finding the null space. A basis for the null space is these 4 vectors. So the span of those 4 vectors makes the null space. All linear combinations of those 4 vectors of the null space. They are already linearly independent. When you do this procedure, they always come out linearly independent, and so they are a basis. I didn't feel like rewriting this. How many vectors are in the column space of A? infinite. There were only 3 in the basis, but the column space of A is made up of linear combinations of the basis using any and all scalars, so there's an infinite. All right, so let's try to come up with an example of a vector that's in the column space of A, but it's not in the basis and is not the vector we gave at the very start of class at in part A, right? 2, 0, 6, -6. So you doubled this one, right? Oh yeah, 2, 0, 6, -6. It's not in the basis though, right? 2, 0, 6, -6. It wasn't in the basis. Any linear combination of vectors in the basis will work. So you could just put a weight of 2 on that guy, zeros on the others. 2, 0, 6, -6 works. Or any linear combination of vectors in the basis for call A. Okay. How about a vector in row A that's not in the basis you gave and not the vector you gave in part A? Row A is not the 0 vector. No, I guess it could be the 0 vector. We're talking about row A, not null A right now. Row of A. We did not give it in part A. Row of A, yep. The row of A is the span of these 3 vectors from R7. And if I put weights of 0 on all of them, I would get a 0 vector in R7. So I could give the 0 vector as my answer to this one. Or any linear combination of vectors in the basis for row A. How about a vector in the null of A that's not in the basis and not the vector you gave in part A? Yeah, so we'd have to take part D here. So we've got a basis. So I can't just grab one of those vectors, though all of them are in the null space. I'm asking for one that's in the null space, but isn't one of these 4 and isn't the 0 vector. You could add them all together. You could add 2 of them together. You could multiply one of them by a scalar. Yeah. Right. Yeah, but no, it also says that's not in the basis. A vector that's not in the basis. Yeah. So yeah, let's take this first one, or no, let's take this last one and double it. That's easy. 0, 0, -2, 0, 0, 0, 2. Put a weight of 2 on that one and 0 on everything else. Or any linear combination of vectors in the basis for null A. Yeah. The basis of a vector space is like the building blocks of the vector space. You can build any vector in the vector space using vectors from the basis, a linear combination of vectors from the basis. Okay, now you can think about some questions.